Cuando usted me diga.
Sí, esperemos un minutito, ya estamos en vivo, pero podemos esperar un minutito antes de comenzar la sesión. Ya le voy a dar el...
Ya. Súper.
Perfecto, ya estamos en vivo, profesor, así que puede presentar a nuestra expositora. Sí.
Yeah. Okay, Ana, I think I will go first in Spanish, and then I will go in English, okay?
Okay.
So, hola, ¿qué tal? Muy buenas tardes a todas y todos. Bienvenidas y bienvenidos a un nuevo seminario en el contexto de los del programa de seminarios anuales que el Grupo de Geotecnia de la Universidad de Chile tiene todos los años, que estamos llevando a cabo desde el año 2016, para una nueva charla el día de hoy con la profesora Ana Chiaradonna de la Universidad de L'Aquila. Esta presentación el día de hoy es en inglés y trata sobre los modelos de generación de exceso de presión de poros que la profesora Chiaradonna ha desarrollado en base a su investigación. Ahora me cambio a inglés. Yeah. Welcome everyone. Thank you for being here at University of Chile with us today. We have this great seminar from Professor Ana Chiaradonna from University of L'Aquila, and she will presenting her work on excess pore pressure development during earthquakes. Professor Ana Chiaradonna is right there in the camera. You can see her. Ana, hello, how are you?
I'm fine. Thank you so much for the
How is everything in Italy? Thank you very much for being here with us today.
Oh, yeah. My pleasure, my pleasure. So first of all, I would like to thank you for inviting me to be part of this seminar series. And I would like to thank you also, your staff, department, your university, because they are doing a great job. So
thank you very much. Thank you very much. I hope you feel comfortable with us here presenting your work. You have been doing a lot of research lately related to earthquake engineering and liquefaction. What are your main interests regarding research?
Yeah,
what have you been doing these years?
Yeah, this is actually, I'm very happy to be here today because this is a great opportunity for me to share the experiences that I gained in the last 5-7 years. So it's just a summary. So I'm very happy to do this seminar today. So this is the topic of the seminar is exactly my main research topic. So okay. Whenever you want, okay. I can start.
And I would just a quick little question. How has been your career? What was your start? Where did you do your PhD? And how did you start in L'Aquila as a professor?
I started 3 years ago in L'Aquila as a research assistant in geotechnical engineering. I did the PhD in geotechnical engineering at the University of Napoli in the southern part of Italy. And then I have some experiences and internship with several research groups around the world. First internship with the University of Washington in Seattle. Another internship was with Mieszko Kubrinoski at the University of Canterbury in New Zealand. And I have a lot of liquefaction there. So it was a very, very nice.
Yes.
And more recently, last year, I was in Davis at the University of California. So there I'll learn a little bit of flag, PM4 sand, PM4 silt with Ross and Katerina. So I tried
with Katerina working?
What you said?
You were in Davis working with Katerina?
Yeah, with Jason de Jong and Ross Boulanger. So I had
nice.
Also a little bit of learning a little bit Flux. So I try to put all these different experiences in this presentation. Just
I see.
try
I
to
see.
provide some useful guidelines, I think.
I see. My understanding is that you are from an area close to Napoli. Do you like the football team of Napoli, maybe?
Yeah. This is my favorite, actually. So
I see. I see. Great. Well, thank you very much. Thank you very much for being with us here. It's really great to have the opportunity to have you presenting your research, your work. And the stage is all yours. I will turn off my camera and my microphone so you can present your work. Thank you very much again, Anna, and see you in a little bit. Thank you.
Okay.
Bye-bye.
Okay. I'm ready to go. So my main goal for the today presentation is just to provide you a general overview of the estimation methods for predicting the earthquake-induced excess water pressure and some practical applications. So at the end of the seminar, you will be aware of the pros and cons of each of them. You will choose the best methodology as a function of the type of problem that you have to solve. So since I don't know what is the background of the audience today, I decided to start from the very beginning. So the main topic is the liquefaction. And the liquefaction is dramatic loss of strength and stiffness resulting from the excess water pressure built up. So looking at the soil element, what is going to happen inside the soil, we have to consider that we have granular soil, which is loose, young, uncemented soil, so with an effective stress state quite low. So we are looking at the shallowest part of the soil profile, and this is also saturated. So when the shaking happens, we have increase of excess water pressure because the loading is applied too fast, and the water has no the time to escape from the voids. So we have an increased of poor water pressure, and after the end of the shaking, it started the dissipation process. So when the excess water pressure is going up, the effective stress state is going down. So at the end of the process, after the end of the dissipation, the soil particles have a new configuration, which not necessarily is more compacted than the original one. But anyway, we have large ground deformation, we have large displacement. So the accumulation of excess water pressure is strictly connected to the observed damage. So from an engineering point of view, we have the key parameter for this seminar or for this problem is the excess water pressure ratio. And the excess water pressure RU is by definition the ratio between the excess water pressure generated by the seismic event, normalize it to the initial effective vertical stress state. So when RU is going to be 1, liquefaction is attenuate. When RU is less than 1, liquefaction is not attenuate. But from an engineering point of view, the crisis of the structure can be attenuate even before the liquefaction, because when RU is going to be close to 1, we have reduction in stiffness and strength. So it means that we have to check as an engineer the safety and the serviceability of our structure. So for example, a very good example are the shallow foundation of residential building. So here are some examples with some damage induced by liquefaction after recent seismic events. And for shallow foundation, we have to check the bearing capacity and the settlements. So for doing so, we need some tools to predict the excess water pressure. And in this, we have a different type of approaches. So first of all, we can identify 2 different families. So we have the decoupled approaches, where the excess water pressure is assessed after the calculation or the seismic response analysis, or decoupled approach, where the pore water pressure are predicting during the shaking, during the analysis. So decoupled approaches are the effective stress analysis. So in the first family, we can have a synthetic prediction. So it means that we are going just to have one number, one synthetic number, through an empirical formulation or RU as a function of the safety factor. Or we can do something a little bit more complicated, which means a prediction of a time history. But in this case, we have to run a total stress analysis in one step, and then a simplified pore water pressure model in a second step. Regarding the decoupled analysis, we can have two different types of groups. The loosely coupled approach, where a simplified pore water pressure model is used in conjunction with the total stress constitutive model. So it's a little bit tricky because we are predicting the pore water pressure model, and then we are going to calculate the effective stress state as the difference between the total stress and the generating pore water pressure. While in the fully coupled approach, we are using an advanced constitutive model where the stress-strain relationship is directly in effective stress. So the exit pore water pressure are calculated as difference between the total stress and the effective stress. So in this table, moving from the top to the bottom, we are going to increase the complexity, but also the accuracy of the methodology. In this presentation, I choose to spend the most of the time talking about the super simplified methodology because it's something that everybody can do. And a little bit about the simplified methods, because I think in the most of the cases, they are not really convenient. And the last part will be relating to the effective stress analysis. I would like to highlight the importance of the effective stress analysis. I don't want to spend time describing one specific model, but I would like to discuss the problem of the calibration, which is the most challenging part in the using an advanced constitutive model. So let's start. This is the summary of the presentation. So I started with the super simplified methodology. And the starting point is the fact that we are using empirical methods for assessing a safety factor against liquefaction. So what is the philosophy? We are, first of all, identified a limit curve, which is the red line, for example, that is going to divide the liquefaction zone from the non-liquefaction zone that is coming from the collection of data from historical past seismic events. Then we are going to identify one parameter, which is I use R1 to say normalized resistance of the soil, which in the most of the cases is the QC1-NCS or the 160CS that is coming from an SPT or a CPT test. The shape is similar because they are the sum of the two different components. The first component is taking into account of the fact that the overburden effective stress is different. And the second part is relating to the fact that there is a certain fines content that is going to play a role in defining the soil resistance against liquefaction. So after one of the two has been calculated, we can go inside the charts. That can be the chart for the SPT or the CPT. We go generically, we go inside the chart and we use the chart to identify what is the cyclic resistance ratio, which is relating to a specific condition, a magnitude 7.5 and an initial effective vertical stress of 1 atmosphere. So to calculate the safety factor, we have to compare the soil resistance with the seismic demand. The seismic demand for us is the cyclic stress ratio, calculating according to this relationship, where Emax is the expected maximum acceleration at the surface. The sigma are the total and effective vertical stress before the shaking. RD is a reduction factor, which is mainly relating to the deformability of my soil column. At this point, I have to normalize the CSR to have exactly the same condition that I have for my resistance, which are magnitude 7.5 and effective vertical stress of 1 atmosphere. So I divided the CRR for the magnitude scaling factor and overburden correction factor. So I have the value that I can compare with the CRR. So I can calculate the safety factor by definition. If the safety factor is less than 1, liquefaction happens. But if the safety factor is more than 1, I know that RU it's no 1, it's less than 1. But how much is RU? If you want to answer this question, because I want to use the RU according to performance-based design approach, I would do the further calculation. We propose a methodology to calculate RU. For doing so, I have to open a little bit bracket because it's very important for the rest, for the remaining part of the presentation that one concept should be clear. So when we think to the empirical charts, we usually use the empirical charts, for example, the CRR as function of QC1 NCS to calculate the safety factor, which is actually what I already said. But in reality, every point of the empirical curve can be used to generate a cyclic resistance curve. In which way? In this way. Because if I have one value of QC1 NCS, I have one value of CRR, which this value, it's one point that I can plot inside the CRR versus the number of cycle plane, because this point is relating to a number of cycle, which is representative of a magnitude of 7.5, which is usually it's 15 number of cycles, some number close to this value. So if I'm going to multiply the CRR for the K sigma, I can also take into account of the effective stress state that can be different from 1 atmosphere. At this point, if you want to change the magnitude, it means that I would like to consider an event which is a magnitude higher or lower. I can multiply this number with the magnitude scaling factor. In this way, I can transform one point with the one cyclic resistance curve. So this curve is analytically described by a relationship such like this, where the shape of the curve, which is ruled by B, it's a function of the normalized resistance, that in this case is QC1 NCS, but it can be also N16 CCS or whatever will be your normalized resistance. So if this concept is clear, we can move forward in the path. We can start from the cyclic resistance curve to calculate the safety factor. First of all, we have to define my seismic action. So after I identify the CSR, I can calculate the safety factor by definition. So I will have the safety factor is more than 1 in this area, and it will be less than 1 in this other area. So I can plot the safety factor as a function of the number of cycle, and the curve can be described, but this function, which is very similar to the previous one, and the shape is still a function of the normalized resistance. At this point, we have to combine this relationship with another one. So let's do another step forward. Generally, we transform an irregular time history of shear stress to a regular one, which is a uniform cyclic time history with an equivalent amplitude and equivalent number of cycles. So as we accept this transformation, we can also accept that an irregular accumulation RU can be represented by a regular function that is coming from experimentation with the cyclic laboratory test. This is analytically described by different relationships. In this paper, we decided to use the Booker et al. 1976 relationship because it requires only one parameter, which is the exponent beta, And beta has been identified to be a function of the fines content and relative density according to experimental data that comes from the Polito relationship, which is only a function of these two parameters, where the relative density, of course, can be estimated by in situ investigation, such as SPT or CPT. So we use this relationship and we combine this relationship with the previous one, where the safety factor is a function of the normalizing number of cycle. A little bit different from the previous one, but it's very simple and similar. So we can combine these two relationships. In this way, we can have a straightforward relationship between RU and the safety factor against liquefaction. Of course, this is can be applied only for safety factor more than one. And we have to identify who is B, who is beta. But B, as we said, it's only function of the normalized soil resistance. So it means the only function of QC1 NCS and 160 CS. And the other parameter, which is beta, is a function of fines content and relative density. So it means that we don't need new input data compared to the data that we have already used to calculate the safety factor. So in this way, calculate an estimation of RU, it's very simple and straightforward. So this analytical expression can be plotted. So in the paper, we have different charts for different amount of fines content. So you can go inside your the chart with your safety factor for different fines content or relative density, and you have the estimation of RU. These analytical curves were validated and verified on laboratory data in the same paper. And we considered 6 different types of soils with different grain size distribution, fines content, and relative density. So we have experimental data. So we know the cyclic resistance curves, and we calculated the RU versus the safety factor of the experimental data and comparing the experimental curve with the analytical ones, which are the red curves. In all the cases, the red line is a little bit above, so this is fine because we want to have a super simplified methodology, so it should be a little bit conservative. And the same approach has been also applied very, very recently to a case history that is coming from the 2020 Samos earthquakes. So these earthquakes happened last year in the north. The epicenter was in the northern to the Samos Island. These are the contour of the PGA obtained using the data, the PGA recording at the station in the western part of Turkey. We can zoom a little bit on the Izmir area because the contours of PGA was highlighted that the PGA recording are higher here. So this is going to identify side effects in the Izmir Bay. But I don't like to talk about the side effect. I would like to talk about a building which is approximately located here. I cannot share all the details because this work is a little bit in progress, which is not published yet. But anyway, there is a building here that during the events has no liquefaction has been observed around the building. But during the construction of the buildings, we realized some stone columns and was observed water eruption from the vertical drains after the shaking. So it means that there was water eruption, but no liquefaction. So try to understand what was happened. We collected data, and this data coming from our friend from Edge University, and he collected the data which coming from the field investigation that were done before the construction of the building. So we know what is the SPT profile, roughly estimation. We know what is the location of foundation depth. we know where are the main characteristics of the drains. So I use the SPT profile data, and I have a rough estimation of the fines content starting from a qualitative description of the soil profile. So I can use the annual 6 ECS to calculate the cyclic resistance ratio and calculate also the safety factor using the maximum acceleration recording around the building at the magnitude of the event, which is 6.6 according to the Turkish government. So in this way, the safety factor is always more than 1. But if I calculate the RU starting from the FS with the curves that I have already described, I'm telling that the expected RU is ranging between 0.2 to 0.7. So there is no liquefaction, but excess water pressure generation. So there is an hydraulic gradient, which is higher enough to induce water eruption. So even though this methodology is extremely simplified, super simplified, it can easy enough, it's able to explain the mechanism observed. So, but anyway, the synthetic prediction has big limitation. So I would like to show the limitation of the super simplified methodology. I would also highlight the importance of carrying out an effective stress analysis in specific cases. So first of all, as Mishko as reporting in his paper, the safety factor does not take into account of the system soil response of a layered soil profile. So it means that every time the RU calculation, if the safety factor is not reliable, also the RU prediction is not reliable. And this is something that we expect because in a layered soil profile, the RU calculation is just the consequences of the safety factor calculation. So if the safety factor is not working, RU prediction is not working as well. So there is also another consideration to do is that during the shaking, depending what are the boundary conditions, we can have variation, redistribution of accessible water pressure, and with a super simplified model, we are not able to take into account of these other important aspects of the phenomenon. So in this case, it's important to do an effective stress analysis according to a loosely coupled or fully coupled, so whatever you prefer. One case history, which is Sendai site, I think it's very useful to understand the importance of an effective stress analysis. So this site has been studied, well investigated during an international project, which is the Presenta project I was involved with during my PhD. So for this site, we have well investigated soil, especially some undisturbed sample in the fine sand layer. We have BS profile and laboratory tests. Also, we have 2 accelerometers, one at 10 meters depth and the other one at the surface. So we use the downhole acceleration time history as input motion for running some numerical analysis. And we try to predict the response at the surface. With my code, I run in 2 types of analysis: total stress analysis, where generation of excess water pressure is not taken into account, and effective stress analysis, which is the red line, where excess water pressure generation is considered. So, of course, you can say it's clearly shown that the excess water pressure it's very important. It's an important aspect of the site response, because in total stress we are going to over-predict the maximum acceleration, while the effective stress analysis is taking into account the fact that where excess water pressure are generating, the soil column is losing stiffness. So we have elongation of the period and the amplification of the motion. So only with an effective stress analysis we are able to catch the real behavior of the soil. So for doing effective stress analysis, we have 2 options. as I already said, loosely coupled and fully coupled. What is the difference? It's more or less the difference between a little car and a big car, because with a big car, you can have just a better performance. So the loosely coupled approach, we are using a constitutive model in total stress, and we are going to predict delta U as function of the accumulation of shear strain, shear stress, or energy. Depending, there are a lot of different types of simplified pool water pressure model. Most of them are implemented in one-dimensional code because it's, you know, it's a big car. It's not a big car, it's a small car. In the fully coupled approach, we have a lot of advanced constitutive model that are going in this second group. I just reported to family, which is probably the most popular. And in bonding surface models, there is also the PM4 PM4 silt, which is probably one of the most popular model for studying liquefaction. So I would like to talk a little bit about a simplified pool water pressure model I developed it during my PhD, and a little bit about the philosophy for the calibration of the advanced constitutive model. So I spent a little bit of time on the simplified pool water pressure model, not because it's my model, but because I think it's a good example to show the difference between a decoupled analysis and a coupled analysis. You can really understand what is the pros and cons of each of them. So the simplified pool water pressure model is called PVP. Requires the definition of two curves. The first curve is the cyclic resistance curves, analytically described by this relationship, where three parameters needs to be defined. Alpha, which is going to control the shape of the curve. The CSR threshold, which is the asymptote of the curve, which means also the value below which accumulation of excess water pressure cannot happen. And NR, which is a reference number of cycle, usually assumed equal to 15. And the CRR, which is the cyclic stress ratio of the reference point. So we have three parameters. And for regarding the second curve, which is the RU as a function of the normalizing number of cycle, we have three parameters, A, B, and D, which are obtaining as best fitting of the laboratory data. So to use this model, you need to have laboratory data that comes from cyclic simple shear test or cyclic triaxial test. Originally, since this is simplified pool water pressure model, is able only to predict the residual excess pool water pressure and not the transient one. So how the model works? After these 6 parameters are defined, you can calculate the damage parameter, which is the accumulation variable. So every time the cyclic stress ratio, which is a normalized stress, is going to overcome the threshold value, the damage is generated. So the damage is something which is proportional to the RU accumulation, because substituting this relationship in the cyclic resistance curve, we can calculate the damage at liquefaction, which is the maximum value. And as a function of the normalized damage parameter, we can have the estimation of RU. This model has a big advantage, is the fact that the normalizing number of cycle is equal to the normalized damage parameter. So it means that I can use the RU versus the normalizing number of cycle empirical relationship. And this previous empirical relationship can be used also in this model. So I choose this specific function because I think it's quite flexible, able to describe the behavior of different types of soils, but you can also use a different relationship. It's going to work as well as this one, because K on KL is equal to N divided by NL. So, but just to be a little bit more technical, if we go inside a soil element, and the soil element is going to be subjected to a time history of the shear stress, such like this, we have first of all to calculate the normalized stress, which is the absolute value of tau divided by the initial effective vertical stress. In this way, we use the normalized stress to calculate damage, because every time the normalized stress is going to overcome the threshold value, we have accumulation of damage. So the damage is a variable that is going to increase or can remain flat. It remains flat when the normalized stress is below the threshold. So after I calculate the damage, I can calculate the normalized damage, because the damage of liquefaction, it's only a function of the cyclic resistance curve. And I can use this relationship to have a prediction of U and consequently a prediction of delta U. So this is what's happening with a regular time history. But if you want to do the same with a real seismic events, we have to do actually a decoupled analysis. A decoupled analysis is carried out in 2 steps. In the first step, we have to do a total stress analysis. So the ingredients are the same of a total stress seismic response analysis. So it means that we have to describe the site in terms of soil stratigraphy, geometry, depth of the bedrock. We have to apply the time history of acceleration. That will be my input motion. I have to define the property of my soil. So I have to define the small strain behavior and the nonlinear and dissipative behavior of each of the layer. Then I have to run the analysis. At the end of the analysis, I have, this is, for example, the maximum shear stress profile. At this point, I have to extract at a certain depth what is the time history of the shear stress. For example, I consider the time history obtained at 5 meters depth. At this point, I have to use this time history in a second step, where I'm going to apply the pool water pressure model on this time history. It means that, as I said again, I have to calculate the normalized stress, and every time the normalized stress is going to overcome the threshold, I have the accumulation of the damage. So I can calculate the normalizing damage. As a function of the normalizing damage, I have the relationship to calculate RU, and consequently, I can calculate the delta U. So the delta U are generating during the strongest part of the shaking. In this specific example, liquefaction is not assigned because the maximum delta U is below the initial effective vertical stress. So this is the process of a decoupled analysis. So it's something that everybody can do, because everybody knows how to run a seismic response analysis, for example, with an open source code. What is the disadvantage? The disadvantage is that it's quite time consuming, because you have to calibrate your model, you have to calibrate, however, your pool water pressure model. So the effort, it's big, but the results, it's something that is not going to satisfy our expectation in the most of the cases. So it's more convenient in most of the cases running directly an effective stress analysis, which is actually a coupled analysis. Just to provide you an example of the differences between a coupled and the decoupled analysis, the pool water pressure model has been implemented inside the computer code for seismic response analysis, which is called the SCOSA. This code is not commercial, it's not yet available. It will be an open source, but it's not available yet. So I don't want to spend too much time talking about the code. The most important message is that since the code, the water pressure model has been implemented inside the code, I'm able to run total stress analysis, effective stress analysis in total and draining condition, and also an effective stress analysis taking into account the dissipation excess of water pressure. So I can perform 3 different types of analysis with the same code, where what is the difference between decoupled and the decoupled? The ingredients are the same, but in the effective stress coupled analysis, there is implemented a degradation models. So in the meantime, I'm going to generate RU during the shaking. I'm consequently reducing the effective stress state, so I'm going to reduce the stiffness on my soil profile, and consequently the response on my soil is going to change through the time. Just to be more clear, I run in 3 different types of RU estimation. The estimation with the decoupled analysis and 2 coupled analysis in undrained and partially draining condition in the same simple ideal soil profile. So in the case of the decoupled analysis, I run it a total stress analysis and then apply the water pressure model offline. In this case, the prediction of RU at a specific depth, in this case 3 meters depth, the prediction from the decoupled analysis is higher than prediction of RU that is coming from decoupled undrained and coupled partially draining. Why this happening? Because during the total stress analysis, I'm not considering the degradation, the reduction of stiffness on my soil profile. So the response of the soil in terms of shear stress, it's higher than what it should be in reality. So this is why the decoupled analysis, it's quite conservative, but since it's quite time consuming as well, and the input data are the same of the decoupled analysis, in the most of the cases, it's better to do decoupled analysis because it's definitely more realistic. So moving forward in the process, I would like to open the discussion about the problem of the calibration of the models for effective stress analysis. Because until now, I said the simplified water pressure model requires some laboratory data, but in the most of the cases, laboratory data are not available for liquefiable soil. So I try to find a calibration process of the simplified water pressure model starting from the field test. So this is what I'm going to discuss in the second part of the presentation. So first of all, I'm considering 3 different types of in-field tests: SPT, CPT, and DMT. Recently, I added also the gelatometer test because gelatometer test has been invented in L'Aquila, which is the university I'm working now. So I decided to add also the DMT test. So the normalized resistance that I'm going to consider is the NO160CS for the CPT, for the SPT, QC1NCS for the CPT, and KD, which is the horizontal stress index, which is obtained by the DMT test. So what is the philosophy that we applied? I think it's important to talk about because the same philosophy can be applied to calibrate also a different type of models. So first of all, I used the empirical charts provided by Boulanger-Idriss for SPT and CPT. And as I said at the beginning of the presentation, I can use these empirical charts to generate some cyclic resistance curves for a defined value of effective stress, for example, 50 kPa in this case. So I have different curves, each of them is relating to one value of NO160CS and QC1NCS. Regarding to the DMT, it was a little bit more tricky because I used this relationship between the QC1NCS and the KD, and we proposed this approach in this paper. So we substitute the QC1NCS with the KD. So actually the red curve is the Boulanger-Idriss CPT empirical relationship, which has been transformed and used for the DMT. But anyway, it is in good agreement with the proposed relationship by Marchetti. And we also, in the same paper, we try to verify the reliability of this assumption. It means that we try to use the red curve to generate a cyclic resistance curve for a real soil, which is located in the northern part of Italy. And it is going very close to the estimation comes from the lab. So we think this is something that we can do. So we use the empirical chart from CPT, SPT, and DMT, basically coming from Boulanger-Idriss 2014 to generate a data set of curves with the different QC1-NCS, N160CS, or KD. After we generated the data set, I apply my model, so I can identify, I can realize some charts where as a function of QC1-NCS here reported, but I have the same for N160CS and KD. You can go inside the charts and identify the three parameters for the cyclic resistance curve. In the same way, we use the pollutant-toll relationship, as I already introduced, and the Booker relationship to generate a data set of excess water pressure ratio curves. And after we generate the data set, we use the relationship on my model to generate some other charts where, as a function of the relative density of fines content, you can straightforward quantify the three parameter A, B, D on my model. So the relative density can be estimated starting from CPT, SPT, or DMT. So again, only the field test is enough to calibrate the parameters on my models. Just to provide you also an application of this simplified calibration procedure, I considered the Port Island case study, which is probably the most popular case history on liquefaction that we have. As you can see, the Port Island is a man-made island, which was realized for install an airport. And during the 1991, a vertical array was installed, and this vertical array was able to record the 1995 Kobe earthquakes that induce widespread liquefaction throughout the first part of the island, which was realized during the first phase of a construction of the island, with a material which is called the Masado soil. The grain size distribution of the Masado soil is here reported, and is a well-graded soil, mostly gravelly soil, and this is the soil that liquefied. But thanks to the vertical array, we have records of the seismic events at the surface, 60 meters depth, 32 meters depth, and 83 meters depth. So what I did for my simulation, I considered the accelerometer on 16 meters, and I used this signal, recording signal, as an input motion on my numerical simulation. So I try to reproduce the records at the surface, carrying out two different types of analysis. A first analysis in total stress, where I just going to identify a VS profile, GGmax and damping curves. I used some literature data for curves for gravelly soil, which are going to match very well the laboratory data that I have. And I also carried out a second effective stress analysis where the water pressure model is considering and is calibrated based on the SPT profile. So let's go to compare the results of the analysis where the recording signal at the surface of the Port Island vertical array is compared with the results of the analysis in total stress and in effective stress state. So of course, in total stress, we are going to overestimate what is the response in effective stress. Even though we use a simplified calibration procedure, we are able to catch what is the PGA and the main mechanism of liquefaction. So The final message is better running an effective stress analysis, even though following a simplified calibration procedure, than running a total stress analysis, because this overestimation is not acceptable in the most of the cases. So after, I would like to open a little bracket regarding to the fully coupled approach, because I'm working with this type of model more recently. And I don't want to talk about a particular model because I'm not the most qualified person, but I would like to talk about the philosophy for the calibration of the fully coupled models. So what is the new trend? What is the new trend for the calibration of these models? So these advanced constitutive models are able to predict both residual and transient exposure pressure, and they are able to predict the post-liquefaction soil behavior, the butterfly loops, the shear strain accumulation. So they are the best that we have. What is the main problem in the use and the application of the advanced constitutive model in the professional practice? The main problem is that the number of parameters that is necessary to calibrate in this advanced constitutive model is generally high. And the main problem is not the total amount. The problem is that most of them have not a clear physical meaning. So it means it's hard to calibrate this parameter. So the new trend in the calibration process, which is the trend followed by Ross and Katerina for PM4 sand, PM4 silt, but also the same philosophy that Miszko Kubrinowski is going to follow for the calibration of his stress density model. It's exactly this sequence. So if we have an advancing constitutive model, we can perform a very rigorous calibration on a well-investigated sand. For example, Atuura sand, because we have monotonic and cyclic laboratory tests. After we have verified that the model is working well, at this point, we can identify the key parameters of the model. It means the primary parameter, which are basically the parameters that are going to control the cyclic resistance curve. After that, we can we can define some relationship between the primary parameters and the in-situ test results in order to have a procedure which can be easily applied in the professional practice. And finally, simple guidelines are provided for the final users. So it means that you have to define the primary parameter, while the secondary parameter can be left to their default value, that this default values comes from the rigorous calibration that I performed at the beginning. So just to provide you an example that comes from the PM4 sand. PM4 sand has 27 input parameters. Here are listed. So, but the philosophy is that only 3 primary parameters, these 3, needs to be calibrated. So, for example, if you want to calibrate the PM4 sand, starting from SPT data, the relative density parameter, is coming from the N160, so it's very easy to define. The shear modulus coefficient can be calibrated on VS measurements because it's relating to the small strain behavior, or if VS measurements are not available, you can use straightforward this empirical relationship. The most challenging parameter is the contraction rate parameter, HP0, which apparently it's hard to calibrate. In reality, it's quite simple because you can go inside the empirical chart with the N160 CS of your problem you have, of your soil. And you are going to identify what is the CRR, your target CRR. It means that the obtained value should be representative of the resistance of your soil for 15 number of cycles, which are the number of cycles relating to a magnitude of 7.5. So what is the process to define HP0? Of course, you need to use a tool to simulate a cyclic laboratory test. In the simulation of the cyclic laboratory test, you have to change the HP naught with a trial and error procedure until the liquefaction is attained for 15 number of cycles. In a cyclic test, when you are going to apply a loading which is equal to the CRR, which is your target. So it's probably more easy to do than the way that I'm explaining the procedure, but I did several times, so it's simple to do. And I also reported a table with the summary of some parameters that can be used for some typical N160 value obtained for liquefiable soil. So after this little bracket, I would like to close the seminar coming back to the initial question. Why it's important to have an estimation of RU? Why it's important to have RU estimation, and what is the utility of RU estimation? And so moving to the last part of the presentation, what we can do after RU has been predicted, for example, with the synthetic prediction. We can do multiple things. First thing, we can calculate the degraded beam capacity of shallow foundation, because there are some simplified relationship proposed by Karamitros et al. 2013, where degraded beam capacity is exactly a function of RU. We can also do an estimation on the free field consolidation settlement. We can use the RU prediction to design liquefaction mitigation measurements. We can, for example, use the RU estimation to quantify what is the uplift force that is going to work on an underground structure which is surrounded by liquefiable soil. We can use RU estimation to also apply a new liquefaction index that has been proposed in this paper. So since the time is flying, I have only a few slides. For one slide for talking about the free field consolidation settlement, which is better explaining in this paper. And I would just like to introduce what is the philosophy, the story of the induced damage parameter, which is a new index to assess the liquefaction potential, which is described in the second paper. So regarding the post-liquefaction consolidation settlement, the current state of practice is just to use the QC1 NCS to go inside this chart, using the curve depending on what is your safety factor against liquefaction, and calculate the post-liquefaction volumetric strain. We are going to do the integration of the strain along the depth, and we have an estimation of settlement. So since this chart is coming from laboratory data carried out on Fuji River sand only, we propose in the paper an estimation of the post-liquefaction consolidation settlement by definition. So by definition, the dissipation of accessible water pressure is going to induce a settlement in 1D condition. So the delta U is coming from dynamic analysis or a simplified relationship, as I already explained it. The most challenging parameter is just the constrained modulus, and I can use different relationship depending what is the shear strain level that I attain it. If liquefaction is not attained, I use the relationship proposed by Robertson and Cabal for starting from CPT. If full liquefaction is attained, we propose this is a very rough estimation of constrained modulus, and we apply it to some case history. One of them is Treasure Island, affected by the Loma earthquakes in 1989. And this is the match between the simulation and the recording spectra at the surface, just because we did both a dynamic analysis and synthetic prediction of RU. This is also the comparison between the estimated settlement in centimeter and the contours of settlement that comes from the measurements, the observation after the events. So more or less, we are in the good order of magnitude. So this is regarding the post-liquefaction consolidation settlement. Moving very quickly to the new liquefaction potential index, I would like only to show what is the new philosophy. So in the traditional approach, which is free field approach, such as the case of the liquefaction potential index, the LPI is a function of the safety factor and a weighting function, which is a function of the depth. So the LPI is a traditional index because we are looking to the vulnerability of the soil profile. So the other is the seismic events, and the risk is just the occurrence of liquefaction. In the new innovative approach, which is the same approach of the liquefaction severity number and the same also philosophy of the induced damage parameter, in this case, we are looking to the vulnerability of the system. We are looking to the vulnerability of the structure. So the other is the applied settlement, and the risk in this case is the occurrence of damage to the structure. So very quickly, the new index is strictly relating to the free field volumetric consolidation settlement. So according to this definition, the volumetric consolidation settlement, there are a lot of simplification reported in the paper, can be quantified roughly as a function of IU. So the combination of the two is the induced damage parameter, which is requires the definition of the geometry of the problem, so the depth and the thickness of the liquefiable layer, and require, of course, an estimation of IU with a simplified or advanced methodology as you prefer. What is an important aspect of this parameter? If the liquefaction is fully attained in my layer, it means RU is equal to 1, and the EIM is going to become geometrical index because it's only function of the thickness of the liquefiable layer and the depth. So it's very, very easy to apply. And we apply the induced damage parameter to another case history that is coming from the northern part of Italy. So this village is called the San Carlo, was affected by liquefaction after the Emilia earthquakes. And we apply the EIM calculation for each vertical where we have SPT data. And we have severe level of EIM where the most of the damaged structure and symbol manifestation were observed. So it seems that is going quite well. Also, the data that's coming from the damaged building were used to classify the type of damage in 3 different levels. And also EIM was used to define some empirical fragility curves for masonry building. The details are reported in this other paper. So the probability that the damage is going to overcome a certain level of damage is reported as a function of the induced damage parameter. So let's go to the concluding remarks for this seminar. This is just some highlights that I would like to communicate with you. So the earthquake-induced expo water pressure are strictly relating to the observed damage. So according to a performance-based design approach, it's important to have an estimation value. And we have different tools with an increasing level of complexities. Of course, depends from the best choice, depending on what kind of problem you have to solve as an engineer. The synthetic prediction is very straightforward because no additional data are required compared to the safety factor calculation. The decoupled dynamic analysis leads to a conservative estimation of excess water pressure, but it's quite time consuming, so it's often not preferable to decoupled analysis. For decoupled analysis, we can have loosely coupled or a fully coupled approach. It means that we have the possibility to predict the stress strain behavior of liquefiable soil with a simplified or a rigorous manner. The spread of the effective stress analysis is strongly connected in the future to the efficacy of the calibration protocols, and the calibration based on in-situ test is going in the right direction. And if I can provide you a suggestion based on my experience, the key parameter in the calibration process is the accurate prediction of the cyclic resistance curves of soil. So try to matching the cyclic resistance curve of the soil should be the target for the calibration of all the models for performing an effective stress analysis. So that's all for today. Thank you so much for your attention. Muchas gracias por su atención. I would like to say you bye with a postcard that is a postcard of L'Aquila, which is the city where my university is. And now I'm more than happy to answer your questions.
Thank you very, very much, Anna. It was a great talk. It was a great presentation. Thank you very much. Very enlightening. A lot of, I'm gonna move the window a little bit here. It was a lot of very, very important concepts. I wonder if there are questions. The floor is completely open to questions for Professor Chiaradonna. Felipe?
Yes, at this moment, we have one question in YouTube by Santiago Castro, who asks, which are typical liquefiable soil and why? And which are typical fine content and compactation degree and why again?
I'm not very sure to understand what is the
I can repeat that.
Okay.
The first question is, which are typical liquefiable soils and why?
Okay, it's relating to the fines content, I mean. So what is the fines content that is typical for liquefiable soils? So the fines content and the role of the fines content, it's quite questionable because there are several research groups that are going to work on the fines content. There is not just one point of view. There are different points of view which are mainly relating to the type of fines content, because we have to distinguish if the fines is plastic or is not plastic. Because depending from the plasticity, you can have an increase or a decrease of the cyclic soil resistance. So I have no answer. It's mainly a question because it depends from the type of soil that you have, depends from the plasticity of the fines that you have. So I think this is one part of the question. I don't know if there is a second part.
The second part is about what number is about of fine content of
okay. I think that the 35%, which is the threshold number that we use for our empirical charts, it's more or less be considering like a threshold value above which the amount of fine is too much and is going to play a role. So more or less below 35%, the soil can still liquefy. But depends what kind of fines you have, of course.
Thank you for the answer. And we have more questions. Jorge Leon asked one, is it possible to use these models to evaluate the excess pore pressure generation in non-plastic soils and with a fine content higher than 50%?
like in tailings, for instance.
Okay. The super simplified approach, which means the IU as function of the safety factor, since it's a very super simplified models, has some limitations, some constraints, and the main constraint is the fact that fines content should be less than 35%. So it's not cannot be applied. So in this case, when your soil is quite challenging, my suggestion is to use something more advanced. So it's better to run, if possible, an effective stress analysis. So in this case, for example, the simplified water pressure model, it's quite flexible. I use it also for silty sand with more than 60% of fine. So for example, the simplified water pressure model, it's very flexible because you need only 2 curves, but you have to be sure that you are using the right curve. This is the most challenging part. So the limitation is not the capability of the model, but limitations which are relating to the characterization of the soil. If you have good data, you can apply for sure the simplified water pressure model. I don't know if it helps.
I suppose to. And the second question by Jorge Leon, is it possible to incorporate the static shear bias to these methodologies?
Yeah, this is a good question. This is nothing that I never think about before. So I have not a clear idea in my mind, but I think yes. I think yes, but not in a simplified way. You have at least moving forward to the decoupled analysis, because in the decoupled analysis, you can add new ingredients quite easily. But in this case, of course, you are doing a conjunction of multiple aspects together. So you need to do something a little bit more advanced in this case.
Okay, thank you for the answer.
Okay,
and
yeah.
in YouTube, we have a lot of regards and felicitations. Congratulations for the presentation.
Oh, okay, thank you so much. I try to summarize a lot of years of research in one presentation. So I'm going, I don't know if it was clear, especially the final part, because I try to compress a lot of different information and paper together.
There is one more question, I think.
Mm-hmm.
Yes, the last one is by Rogelio Castro, and asks how it influenced the taking of soil samples in dry weather.
Dry weather? Can you say again? I'm sorry.
Yes, dry weather.
Dry weather. So it was meaning. What is the meaning of the question? So
without water, I think.
Without water. So without water, everything is simple, because when you apply the cyclic loading, the grain size, the particle would like to move, and they can move because there is no water. So when you apply the cyclic loading, you have just the same that happens when you are going to vibrate your sample in the lab. You are going just to induce a new configuration, but there is of course no excess for water pressure because there is no water.
Okay, thank you.
May I ask you questions?
Of course.
Thank you. Very nice presentation, Anna. Congratulations. Very good.
Oh, I can see your face as well.
My camera is not working.
Okay.
Anna, I am too ugly. My question, you said that the cyclic resistance curve is one of the most important parameter, let's say, for your model.
Mhm.
But usually that curve is very depending on the sample preparation if we don't have undisturbed samples. And also you may run those tests using cyclic triaxial or simple shear.
Yeah.
So you have a really tremendous differences playing with the preparation of the sample and also with the type of test that you are doing.
Yeah.
So if that is very important, which is your recommendation for the best approach, for the best results using your model?
Yeah, thank you so much for this question. Thank you so much, Ramon. This is a very important point. So really thank you for this question. This is also, I totally agree with what you said. This is why at a certain point, we also try to constrain the calibration to the in situ test, because of course, in the laboratory, there are a lot of different aspects that needs to be taken into account. For example, I did for the Sentai site, I use it in, I show in the presentation. For Sentai site, I had the cyclic triaxial test, and I'm able to simulate only simple shear condition. So I have to convert and I apply the Castro coefficient to try to transform the triaxial cyclic condition to the cyclic simple shear condition. So there are it's real, the problem that you underline. So the cyclic resistance curve, it's very it's a function of a lot of stuff. So my suggestion is try to select the condition which is more close to the site, more than the lab. And probably the best way to do so is try to double check the laboratory data based on the in-field investigation. This could be one possibility, double check the data between field and lab. Of course, at the certain moment, you have to do the best decision, depending who is higher, who is below. You can do sensitive analysis. In any way, you have to constrain your problem. You have to identify what is the sensitivity of each parameter, and at the end, you are the engineer, so you pick the final number. But my suggestion, you try to find condition, to double check the data and try to be as close as possible to the in situ condition that you have for your site. I don't know what you think.
Yeah, thank you very much. Yeah, thank you, Anna. But that is, it's a very important point, because some people just run models and they don't care about testing.
Yeah, sure.
And of course, the input is very important in any model. The model, it is important, of course, but also the input for those models.
Yeah.
Thank you.
Thank you.
Are there more questions, Felipe? Maybe.
Yes, we have two questions in YouTube. And the first one is by Ronald Landia, and asks, is it possible to estimate which would be the max excess PWP at an specified stress level for a fixed pressure hydrostatic head? It is if U0 equal 10 kilopascals or 100 kilopascals, the delta U will be different.
I'm not sure again to have understand properly the question.
Let me help you a little bit. Let me complement a little bit. Complement what Felipe said is, which would be the maximum excess pore pressure at a specific stress level for a fixed pressure hydrostatic head. For instance,
okay.
if the hydrostatic pore pressure is 10 kPa or 100 kPa, would delta U be different?
Okay, the key point, it's not the hydrostatic pressure. The key parameter is the effective stress state. So it's depending where you are. So of course, the maximum RU that you can reach is 1. When RU is 1, well, it means that the maximum delta U is the effective vertical stress.
Is the excess pore pressure
yeah.
over the hydrostatic, right? So
yeah.
I think that's what the question was about.
Yeah, this is the mechanism.
Yeah. And the second question, Felipe?
Yes, by Vicente San Martin. Good presentation. And what is the input data in situ test and or intensity measures required to compute downslot IM?
Okay, this is relating to the new index, which is the one. I come back to the slide, so we can come back to this is the general formulation for the IM. So what you need, it's the RU estimation. So estimation of RU that comes from one of the methodology that we said during the presentation. So you can do the syntactic prediction, which is probably the most quick way to quantify RU, because you have your profile of Fs. From the safety factor, you can straightforward have an estimation of RU. So this is the first part. The other two parameters that you need to as input data are just the depth of the uppermost saturated liquefiable layer. So let's think about that your case is this one. So your liquefiable layer is just the part of the sand layer which is fully saturated. So in this case, this is the minimum depth. So this is the first input data. The second input data, it's the maximum depth of your liquefiable layer. So you only need to know what is the geometry of the problem. This is enough to calculate the induced damage parameter.
Anna, and
there are many questions coming.
Only the first liquefiable layer?
What you said?
If you consider only the first layer who is liquefiable.
The question is aimed at addressing if the models implemented, particularly with the IAM, is aimed only at the first liquefiable layer, and if it does, why?
Okay.
I think that's my interpretation of the question.
Okay. Now I understand. This is a very good question, actually, because this is a point that where I'm not totally sure. So I'm not totally sure about the answer, because in the paper, we have used the uppermost saturated layer. So in the published version, you have to identify only the first liquefiable layer, and you have to neglect what is going to happen below. In reality, I'm performing some sensitivity analysis to verify if this assumption is reliable or not. I have not a clear answer, but my feeling again is that depends, because if the liquefaction, if the system soil response, as reported by Mishko, is going to be triggering, you can have a total misprediction of the reality. Because, for example, liquefaction can happen in the depth and you cannot have liquefaction in the shallowest part. So I think also in the EIM definition, in some way you have to take into account of the system soil response. So the question is something between yes and no at this moment. So actually we identify the uppermost saturated layer, but for example, if you have this layer and you have a little tiny non-liquefiable layer, and then you have another big layer of liquefiable soil, my suggestion is to consider the full system. But I cannot ask for answer in general. I have to say one-to-one on the specific case to provide my suggestion.
Nice. Nice.
Okay. And we have another question by
three more questions, 2 more questions, Felipe.
Okay. By Samir, who asks, nowadays, what is the laboratory test that best simulate the study behavior of soil in relation to the earthquake?
What is the best laboratory data for liquefiable soil?
Laboratory test.
Laboratory test.
Who simulates the behavior in the earthquake? Behavior of soil.
The cyclic simple shear test is for sure the most the laboratory test that is going to be closer to what is going to happen inside. So, but working with the cyclic simple shear, it's very challenging. I have one friend of mine that did his PhD working with the simple shear device, and he's going to be crazy at the end of the program, because it's quite hard to use a cyclic simple shear device. So it's definitely more challenging than the cyclic triaxial test. So this is the reason why probably the cyclic triaxial test is more popular, because it's easy to control the cyclic loading in this case. Of course, there are, for example, some conversion factor, for example, correction proposed by Castro to move from one condition to the other. This is what I usually did when I have to apply, I have to calibrate my simplified pool water pressure model on cyclic laboratory tests. But, you know, if you have the cyclic simple shear test, it's better, for sure.
Thank you. And we have the last question by Juan Manuel Barbailata, who asks, what is the less amount of information that you think is necessary to make a quite good approach to the power water pressure in a liquefiable layer? The minimum amount.
Minimum amount. So the very, very minimum amount, it's at least a reliable in situ investigation. And in the past, I was I was thinking that laboratory data are necessary, but now I'm moving forward field investigation, because also the recent experiences that I have with centrifuge in Davis, we have the possibility to do a field test, simulate like a field test in centrifuge in the liquefiable layer. And we have the possibility to do a very well characterization also of the same sand in lab. When we try to apply, in this case, I'm going to apply an effective stress, a fully coupled constitutive model, because I use it PM for sand in FLAC. At the end of the story, the calibration based on lab data provides an underestimation of the response compared to the field test. So for certain type of soil, which are basically the liquefiable soil, probably it's hard to have very good data in lab. So I believe more in the field investigation, which is also the what Ross said to me the first time I have a discussion with him about the calibration of advanced custody model. So the minimum amount is, of course, a good field investigation. Probably CPT data are better than the others type because we gained a lot of experience with the CPT, especially after the Canterbury earthquake sequences. We have a huge database for CPT that is coming from Christchurch, another huge data set that is coming from Emilia. So we have very nice experience with the CPT. We cannot do the same with the other tests. For example, for the DMT, we have big uncertainties in the curves to use for the safety factor calculation because we don't have enough data. So we are trying to collect data to do a better job. But of course, the CPT, it's the best. So if you can choose what kind of field test you want, I suggest go for a CPT.
Great. Yeah, I don't think we have more questions, and we have had a lot of questions for you already. So thank you very much. Maybe I can make some questions via email. So thank you very much. Thank you very much. It's been such a complete presentation. We have had field data, numerical data, laboratory data. It's been really nice to see all the contributions that you have made to our field. It's really nice indeed to see all that data put together, contextualize it, and give a proper interpretation of the results. It's been really nice, and thank you very much. We really appreciate the time you took to share with us your knowledge. I think this is a brand new presentation, actually, right? There are some of the results that you are showing them for the first time.
Yeah,
right?
yeah, absolutely. Only for you, Felipe.
So thank you very much. We really appreciate the time you took to put this presentation together, and we look forward to hearing from you very soon, to reading your papers, and to all the audience through YouTube and also through Zoom. Thank you very much for your attendance. The live session led by Carlos on YouTube will be shut down now. We say thank you and bye-bye. See you by the end of October. Now I will speak a little bit in Spanish. Muchas gracias a todos los que vinieron para acá a compartir con nosotros esta sesión geotécnica junto a Ana Chiaradonna. Última semana de octubre va a estar con nosotros el profesor Sebastián Boldrini, un profesor que siempre nos apoya mucho aquí en el grupo de Geotecnia de la Universidad de Chile, y va a estar hablando sobre geotecnia aplicada en sectores urbanos. Probablemente vamos a tener una entretenidísima charla sobre pilotes y fundaciones. Así que muchas gracias a todos. Próximamente, we stay here talking a little bit longer with Professor Ana Chiaradonna.